All right. Okay, so chapter 1 is kind of an overview of computers and of programming languages and just a little bit of background knowledge on things like hardware and software and how data is stored inside the computer and how programming languages work and stuff like that. It's kind of, in some ways, it's kind of an introduction to computers and computer science all in one chapter. So anyway. So we'll talk about some hardware and software. I've got my museum of old computer parts over here we can bust out and look at some stuff. And again, we'll look at some evolution of programming languages and talk about what compilers do. And I'll maybe tell you a little bit about the history of C++ as well. Also, a little bit about the difference between structured design and object-oriented design. All right, so computer science, basically, what is computer science, right? Somebody will probably ask you that at some point in time. And so the logical comeback answer is computer science is the science of computers, right? But no, computer science is really, it focuses on problem solving, right? And we just happen to solve problems and implement solutions to problems using a tool called the computer, typically, or some kind of electronic device or something. But it's really about problem solving and implementing those problems, usually in some kind of using some kind of programming language. Okay. C++ is one of those programming languages, but there's lots of others out there as well. As far as good languages to learn at first, I think C++ is an excellent language to learn. Java is also a good one to learn. And so most colleges and universities, when you take the programming sequence, most colleges and universities that I've seen are typically use one of those two languages for their main sequence of courses. Let's talk a little bit of history, right? So before we had electronic computers, we had people invented different types of mechanical types of devices that could help with things like calculations and stuff like that. So are you familiar with these? We can Google some pictures as well. Everybody knows what an abacus is. You may have had one as a child. It's the thing with the beads on it, right? Right. There's even a kid there playing with one. Right. So, but it's basically like a counting device, right? So, you can count by moving beads over from one side to the other. So that's the idea. You could even do things like keep track of maybe ones places and tens place and hundreds place and stuff like that. All right. And then, what else do we have? How about the Pascaline? Have you heard of that? So there was a guy named Blaise Pascal that invented and built this thing called the Pascaline. And it's got like gears and dials in it. But there was no electricity or anything back then at this point in time. So this predates all that. So it looks something like this. And they actually created there's a programming language called Pascal that's named after Blaise Pascal. So, and actually my first college computer programming class was in the Pascal language. So how about, where am I? How about the Leibniz device. It's similar, I think, to the Pascaline. Leibniz. Gosh, I'm a horrible speller. How is it? Leib. Leibniz calculator. I'd probably get it for us. So it's similar, it has like gears and dials and stuff like that inside of it. And then there's a guy named Charles Babbage that had a couple of devices that he came up with, the difference engine and the analytic engine. Difference engine. So notice they're getting a little bit bigger. That's kind of an interesting picture. Get a sense of scale on it, on that one. I wonder where that is. I wonder if that's the Computer History Museum. Anyway. And what was it? The analytic engine? So it's similar, right? Similar looking device. Then there was this one that I skipped over, Jacquard's weaving looms, right? Are you familiar with that? So, yes, it's a weaving loom, and what do you do with looms? You create like fabric, right? It weaves fabric together. So that's kind of a strange thing to have in computer science history, right? And so, what's the significance of that? Not that. So, the significant thing as far as computer science goes with the weaving loom was that the thing is programmable. So it could use these things called punch cards. And so you could use punch cards, which are little cards, and you could basically come up with designs for design patterns for the loom to weave. And you could feed in those or basically tell it what to do with those punch cards. And early day electronic computers actually use punch cards. Similar, I've got a couple in the box over there. So you could, instead of typing on early day electronic computers, instead of typing all your source code and stuff like that and then just compiling it on the computer, you'd basically use these punch cards. You'd have instruction cards that would have instructions on them, obviously, and then you'd have data cards for if you're going to input data, and you'd have like a big stack of these things, and you have to feed them into a card reader, and then the computer would execute it that way. Luckily, that was before my time. But I've heard plenty of stories and horror stories, like if one of those cards got out of order or something like that, it could wreak havoc on your computer program. But anyway, that's the significance with the weaving loom. Herman Hollerith, let's see what his machine looked like. Hollerith machine. Oh, okay, cool. So it'll look more like that. Yeah. A good movie to watch if you're interested in the history of computer science. Have you seen that? Is it the Imagination Game, or is it the Imitation Game? What's the name of that movie? The Imitation Game? Yeah, so, and it's got, what's his name? What's the actor's name? Benedict Cumberbatch, right? He plays Alan Turing in this movie, and it's kind of a story that focuses around him and his life, but also mainly about the efforts of him and his group to break the code of the German Enigma machine during World War II. And basically, he creates a computer that can basically help with the breaking of the Enigma machine code and stuff like that. So, Yeah, it's very interesting. It used to be on Netflix. I don't know if it still is or not. They may have taken it off. But anyway. So those are some early day mechanical computers, right? But then, around World War II time and post-World War II, they started developing and creating and building electronic computers. And so a lot of these early day electronic computers might have been used for things like military projects, like calculating ballistic missile tables and stuff like that. Another good movie I just thought of was that Hidden Figures movie about 3 African American women who are what they called computers back then. Computers used to be people, right? People who did computing, like mathematical computations and stuff like that. So that movie focuses around them, but also gets into the world of computers, and because the group that they're working with, it revolves also around NASA, right? So, and the early space missions and stuff. So they get this IBM computer, and they have to figure out and learn how to use it. And one of them takes it upon themselves to learn how to use this new technology and stuff. So anyway, that's a really good movie too. I just thought of. So what did some of these machines look like the Mark I and ENIAC? Let's do a Google search on those. Mark I computer. A lot of these were really big, right? And they take up like a whole room. This kind of first generation of electronic computers, most of them use vacuum tubes, which are kind of like light bulbs, and they could burn out and they'd get hot, so they had to have special cooling systems and air conditioners and stuff to cool the room, those types of things. So, but they look really cool, don't they? Your iPhone probably has more computing power than that does. ENIAC was another one. Similar type of thing. Oh, that's I don't think I've seen that picture before. Check that out. Yeah, that's cool. See those panels they're holding? You can see the vacuum tubes on them, right? Like on the top and stuff. That's cool. And by the way, if you ever get a chance, if you ever happen to be out in California in that Silicon Valley area, in Mountain View, California, where Google has its headquarters, there's this place called the Computer History Museum, and basically they've got anything that you can think of that is involved with the history of computers and stuff. And they have a part of ENIAC there that you can actually see, and then they have like a UNIVAC. They have a Cray supercomputer in the lobby of the place that you can sit on and take your picture. They've got 2 or 3 Cray supercomputers in the museum. So anyway, it's very, very cool. What are some others there? They mentioned the von Neumann architecture, and John von Neumann was an early day pioneer in computers. UNIVAC, that one looked more like a desk. So that one came out a little bit later, probably like in the 50s. But it looked more like this. What is that? If I remember correctly, they used UNIVAC to help predict the Eisenhower presidential election or something like that. I think that was around that time. So, what else? Transistors and microprocessors. So they mentioned that here. Gotta go back to this. So early day computers used vacuum tubes, and then kind of the second generation of computers, they started using transistors, which is a different technology, and it made them faster and more reliable. So some of those kind of second generation machines are going to use those. But then newer computers started using these things called microprocessors. This is kind of like our third generation, I guess you could say, of computers. And that's what we still have these days, right? So your central processing unit or CPU is going to be on a microprocessor. It's going to be on a computer chip, right? An integrated circuit. So, all right. One thing that sometimes we do, we like to categorize things. So if you're going to categorize different types of computers, these might be some general categories, but you could do it. There's other categories as well, and you can kind of categorize them by maybe things like how powerful they are, how many, what they're designed to do as far as like simultaneous users, how expensive they are, things like that. So mainframe computers were very popular back in the 60s and 70s, and the idea with a mainframe computer is that you have like one main computer, right, that does all the processing and has all the main storage for your computer system. And then maybe you have all your employees at your company that have their individual desk, but they don't have their own personal computer with its own hard drive and things like that. They just have a terminal, you know. And so a terminal, or a dumb terminal, sometimes they'd call it, basically would just have like a keyboard, right, and a monitor type of thing, and maybe some kind of dumb terminal type of, or thin client type of box or something that connects to the mainframe. But it's not designed to have its own storage and do its own processing. All that takes place on the mainframe. So that's kind of how things were for a long time. But then in the 80s, when they started coming up with like the IBM personal computer, IBM PC, and Apple started making things like Macs and stuff, the shift kind of went to everybody having their own personal computer, right? And those are microcomputers and things. A mid-sized computer would be kind of in between that, right? So maybe some kind of workstation, like souped-up workstation that has more processing capabilities and things like that. Remember Silicon Graphics back in the 80s and 90s had their kind of mid-size computers and stuff. We also have supercomputers, right? Which supercomputers they're not really the same thing as the mainframe computers. The idea with the mainframes is that it can support all these simultaneous users that share the resources and stuff. But a supercomputer is designed to be able to do a lot of processing, a lot of number crunching, and perform a lot of execute a lot of instructions, right, in a fast amount of time. So supercomputers, some of the best examples are like the Cray supercomputers, right? So there was a guy named Seymour Cray that basically built a company around supercomputers. Here he is right there. There's Seymour Cray. Where'd he go? Lost him. There he is, with sporting the awesome looking 70s leisure suit there. But anyway, that's an example of a Cray supercomputer. And the cool thing about the Crays, early day Crays especially, like that, not only is it a supercomputer, it's also a piece of furniture that you can sit on. So, like I said, at the Computer History Museum in Mountain View, they've got 2 or 3 of these things, and there's one in the lobby that you can get a closer look at. But yeah, the inside is has all kinds of wiring stuff up there in that middle part, and then the bottom part, the bench part, has like a cooling system with all kinds of pipes and stuff running through there to help cool the thing. Let me close some of these. So let's see if we can. There's a good picture. Oh, check it out. How about that one? Yeah, so check that out. So you can see, like, this is the bench part, and so that's like has a lot of the cooling system stuff in there, And then this has like a lot of the wiring and stuff. So they still use a lot of supercomputers for different things. So he typically use supercomputers for things like weather forecasting and stock market prediction, scientific projects, research projects, and stuff like that. Obviously, they're going to be really expensive. We have a supercomputer project here at the college, actually. It's like it's designed like a Beowulf cluster, Linux cluster. So the idea is that you have several different machines, and you can write a computer program that can basically distribute the program to different processors, and they run in parallel. So that's the idea with that type of system. Most of the supercomputers these days, they look more like this. They're more in these racks and stuff. Where was it? There you go. But Cray, I mean, obviously Seymour Cray isn't living anymore, but his company's still around. So, especially in August and September when we have hurricanes coming through, and they talk about the forecasting the path, predicting the path of the hurricanes, and they have the different models. Well, those are the types of computers and stuff that they run those simulations on. All right. And then, of course, we have embedded computers, right? So these days, you have computers in all kinds of devices, whether it be your smart TV or your car or whatever. There's all kinds of embedded computers that are running that we don't usually even think about. So, all right, let's move on. Hardware and software. So hardware are like the physical components of a computer, and software are the programs that run on the hardware. In this course, we'll be focusing on software. We're going to be creating computer programs, and that's basically software. But let's spend a little bit of time talking about hardware. And this is when I'll bust out my box here. Let's see. Hopefully the box won't collapse on me. The box is a piece of history itself. It's a dot matrix printer box. So it's So a few of the things that we'll talk about are the central processing unit, main memory or random access memory, secondary storage, and input-output devices. All right, so I'll get some of this on video as well. So if you were to open up your computer, and of course this is going to look different depending on what type of computer it is, right? Whether it be a desktop or a laptop or whatever. This comes from that small form factor case that I have up there, that shuttle box. This thing is about 20 years old. And it stopped working on me, so I took it apart. I use it for demos now. But if you open your computer, you're going to have this main circuit board here, right? And what's that called? That's your motherboard, right? So this is the motherboard. Basically, everything plugs, for the most part, plugs into the motherboard in some way. So it has some things that plug directly into it. On the back, you have ports, right, for plugging in other like peripheral devices and things like that. And also, there's all kinds of circuitry on the board itself, that does things. You have like buses that connect different pieces together, right? But one thing that you're going to have on there is your central processing unit, or CPU, which is the main brain for the computer. So it looks something like this, right? So this is the AMD Athlon processor back from the early 2000s. Your main manufacturers of processors are what? What companies have you heard of?
Intel and AMD.
Right. So Intel is probably the biggest name, and then AMD also makes processors. And those are the two main manufacturers that you're going to see. All right. And so if you're going to build your own computer, you put that onto the motherboard, right? And the CPU does all the main processing for your computer, and we'll talk about some of the parts here in a second. But then they can also get kind of hot. You don't want them to overheat, because it's one of the most expensive things that you have in your computer. So usually you'd put like some kind of heat sink compound, like a putty type of stuff on top of it. And you'll probably have like a heat sink that's supposed to help channel heat away from the processor, and usually have some kind of fan on top of that kind of blows the heat away. This one was kind of weird. And actually, I think the processor pooped out. So, I mean, I'm not quite sure. But anyway, this one had this weird heat sink. I haven't really seen these on many computers. But the idea is that you put this on top of the processor, and this was supposed to channel heat away from the processor. And then there was a fan on the back that would blow the heat out. At least that's how it was supposed to work. So, right. And then also on the motherboard, you plug in your main memory, your random access memory, and it usually looks something like this. And it would go in there. I don't think this actually goes with this computer, but you'd put it in there and you would lock it down. And typically, the more of this that you have, the faster things run. Although there are other factors that influence how fast your computer is, right? Including the processor. Right? So they mentioned that the CPU, or central processing unit, carries out arithmetic and logical operations. That's done by a part of the CPU called the ALU, arithmetic logic unit. Other parts you have, let me see if there's a slide on this. No. You have some other things like the control unit. The control unit is kind of like the traffic cop for the processor. It basically controls, which things are coming in and which things are going out. And so processors have this thing called an instruction set. And the instruction set is basically a list of all the instructions that it's capable of executing, right? And so typically the process is something like this. There's all these instructions for a program that are out there, and they're waiting to be done inside of main memory here. But the processor, if we're to simplify things, can only do one at a time. So there's this thing called the fetch execution cycle. Let's see if I have a slide on that. No, I don't. The fetch execution cycle is this process where basically the processor fetches or retrieves an instruction from memory. It pulls it in, decodes it, and then executes the instruction, and then writes the result back out to main memory, right? And so when we talk about how fast a processor is, we usually talk in terms of how many of those execution cycles that it can do in a certain amount of time. So like one of those execution cycles, or sometimes we call them instruction cycles, if a processor could do one of those in 1 second, that would be 1 hertz. So we measure things in hertz, or cycles per second. So 1 hertz would be incredibly slow. And so usually we're talking about megahertz or gigahertz or something like that. So, so like this processor right here, this is an original Intel Pentium 1 processor. And on there it actually says 66. So I believe that this was a 66 megahertz processor. And so that means that it could do around 66 million of those instruction cycles in 1 second, which sounds fast, but actually these days this would be really slow, right? And so, these days we'll talk about, gigahertz, which is around 1 billion. So if you had like a 3 gigahertz processor, that would be about 3 billion cycles per second, right? Of course, it's more complicated than that because there's ways that the processor manufacturers have come up with different ways to make things faster, right? So these days we have multi-core processors, right? So it's kind of like having several processors in one processor, so that can speed stuff up, kind of splits things up between cores and stuff. There's also other techniques like pipelining. I think the book might mention pipelining. So the idea with pipelining is that during this fetch execution cycle, maybe it fetches an instruction and executes it, and then while it's writing the result back to main memory, it's starting the next cycle before technically the previous cycle is finished. So you do that a few billion times and it can speed stuff up, right? So, and there's also other parts to processors like registers. Registers are like real temporary memory locations that are on the actual processor to store data and instructions and things. So if you ever take a machine organization and assembly language course, which is part of most computer science curriculums at the university level, you'll learn about things like that. Okay. So anyway, we'll pass that around. Oh, this is an AMD K6-2 processor. I had a Pentium 2. So this one looks a little bit different, right? The Pentium 2. So, but if it's actually in this plastic case, but in the middle of it, the processor part is there. It's going to look similar to this. So I remember I did a big research paper on this thing back when I was in graduate school. Pass those around. And again, if you're in the Java class, you probably saw those on Tuesday anyway. Let me do a couple of Google searches. So there was the Pentium. Oh, there's the Pentium Pro. Here's the original Pentium, I guess. Here is the Pentium 2 down there. Right. And somewhere I actually have a Pentium 4. So, all right. How about main memory? So that's this stuff. All right, so it looks something like that. And whenever you turn your computer on, the first thing that usually happens is your computer loads your operating system from the hard drive into main memory. So all programs and data and instructions go through main memory before they can get executed, right? So let me pass that around. And so one thing that we'll be talking about a lot this semester are memory concepts. And in fact, in computer science, especially this programming sequence, having a good understanding of memory concepts is crucial, especially when you get later on into like data structures and these more advanced data structures like linked list and stacks and queues and binary trees and stuff like that. We end up using something called pointers. And pointers, it's all about memory and how things are organized in memory. So basically, I'll just mention a couple things. Memory is basically split up into different locations and cells and stuff that can store different things. And each of those memory locations has something called an address, right? And the operating system, your operating system like Windows, can store things, whether it be computer programs that you're running, a game or whatever, or data that you have loaded up. It keeps track of what's what and where it's located by keeping track of those memory addresses. Right? So anyway, the classic analogy is like a post office box. So, if you ever walk into a post office, and one of the first things you probably see is that it's like a wall, right, with a whole bunch of different post office boxes or P.O. boxes, and each one of those has a number on it, an address, right? So that's how the post office people keep track of where to put stuff, right? And when you go to check your mail, if you have a P.O. box, you go to the one that you have been assigned and you know the address for. Right? Also, main memory is volatile memory or temporary memory, right? We often say, meaning that you have to have power to the computer in order for things to stay in there. So if your computer loses power, then you lose what's stored in main memory or random access memory, right? So that's why we have to have secondary storage devices to store things on a more permanent basis, right? So the most common types of secondary storage devices are things like hard drives, right? So everybody knows what that looks like. Hard drive. So something like that. So here you go. Here's some hard drives and different secondary storage devices. So this is a 5 1/4 inch drive. This is probably like a 40 megabyte hard drive. But what's cool about it is the top's been taken off and there's some plexiglass on the top. So you can see the disk platters inside and how get a better idea about how they work, right? So to access different files in different places on the drive, right? The disks spin, and you've got this thing called a read-write head that can move in and out to access the different parts of the disk, right? And the read-write head gets really close to the disk, but it's not supposed to touch it. Otherwise, you get a head crash, which can mess up your computer. And so this is a 3 1/2 inch. This is more of a traditional hard drive. And this is part of it. Obviously, this thing is toast. But you can pass that around. And of course, these days we have solid state drives, right? Which is the way to go. So solid state hard drives don't have those moving parts. So do you guys, what kind of hard drive do you have on your computers? I asked that in the Java class the other day. So
I just changed mine from a hard disk to a solid state.
To solid state?
Hard drive crashed on me. I wanted to run a hybrid, but that'd be the best thing to run in them.
Yeah, so solid state drives, they don't have moving parts, so it's more like a flash drive type of technology, right? And they've come down a lot in price. It used to be one of those things that they were a lot more expensive than your traditional drives. You can still get more storage capacity on a traditional drive than a solid state drive, but the prices come down so much that it's worth it, I think. And they're faster. They use less power, and because they don't have all those moving parts, they're ideal for things like laptops, right? You think about laptops, how much you move them around and jostle them around and stuff like that. That's not, that's not an ideal situation for a traditional hard drive that has moving parts in it and stuff. So anyway, solid state's where it's at. And like I said, you can find good deals on them sometimes around Black Friday and times like that. So And they even make some solid state drives that look more like memory things, right? Like probably like that. But if you were to, let's just look on Amazon.
There's two different ways you can install a solid state drive. You can either put it in a metal casing, but there's some computers that have a little slot like you said where it looks just like memory where you can slide it in.
Mm-hmm.
I think it's a 2.5 slot or something like that.
Yeah. So these are the more common ones probably. They're 2.5 inch in size. So that's gonna be the usual size for a laptop drive anyway. So if you're putting one in a laptop, you'd probably just replace your traditional drive with one of those. But if you're going to put it in a desktop, those are usually 3.5 inch size. So there's usually an adapter that you can get, like a little bracket type thing that you put that in there and then just put it in the spot. But yeah, this is the other kind. So if some motherboards and stuff might support that as well. It looks more like a memory module, but it's actually a hard drive, which is pretty cool. But yeah, right now these are some of the prices. So what is that? Yeah, it's like a 500 gigabyte solid state drive, one of these Samsung, which are very popular, for $80. That's pretty good, and then it's not even Christmas time, right? Because that used to be, well over $100. And so let's see. I bet if we select that, I bet they have different capacities.
They have, I think up to 2 terabytes, I believe, maybe a terabyte.
How much is the terabyte? 150. I bought a 1 terabyte SSD. I bought that one. I can't remember how much I paid for it though. I bought it. It was a Black Friday deal, and it was cheaper than that, but I can't remember how much it was.
I bought the 500 one, I think, for about it's 80 right now. I think I bought it for about 50 on around
Yeah. So, and you could also do both. Some people might do something like have a solid state drive to store things like their operating system and more commonly used programs and stuff that they're going to use a lot, so it'll load up faster. But then they might have a second hard drive that's the traditional drive that might have a larger capacity, like a 4 terabyte size or something like that, for storing things like pictures and things and maybe videos that take up a lot of space. And so that's pretty common to see as well. All right. So how about some other secondary storage devices? If we look back in history a little bit. Of course, there's USB drives, right? Everybody knows what those look like. They come in different forms and stuff like that. These cruiser drives have always been really popular. I've been using some of these little SanDisk Fit ones, I think. They're tiny, yeah. They're more like this. So like I got one right here. I don't think I'm using this. It's like that. It takes up like no space at all, right? It looks a lot like the Bluetooth things for your mouse or whatever, right? But these are great. So I've got a whole bunch of those. All right. Before that, we had some things like in the old days, we had floppy disk, right? So 8-inch floppy disk. So those things were pretty big. Here's a good picture of one. And I have one here. But these are great. So you can see why they call them floppy disk, right? Because they're very floppy. This is an 8-inch floppy disk. And then we also, later on, we had a 5.25-inch disk, like that. This is what we had when I was a kid. And then later on, they came out with the 3.5-inch floppies, which you may have seen, or maybe even your parents had some of these. And I'll pass those around. But they all pretty much work the same way. All right, there's your 5 1/4 inch and your 3 1/2. Right, the 3 1/2 inch floppy disk would store. You could store about 1.44 megabytes worth of stuff on there, which is not very much, right? So, in terms of how big that is, if you're talking about like a MP3 file or something like that, a music file, compressed music file, right? That compresses the size down. You're talking about like, no more than 2 minutes of audio, that you can store on a 1.44 megabyte floppy. Maybe about a couple of pictures or something like that. Not much, hardly at all. Right. So, and this was the time before we had USB flash drives. So there was actually a company called iOmega that came out with this thing called a zip disk. Have y'all seen that? If you were in my Java class, you saw one. They look like this. So they're a little bit bigger than a floppy disk, but and a little bit thicker. So, but this is where it was at back in the mid to late 90s. Compared, 3 1/2 inch floppy could hold 1.44 megabytes stuff. One of these could hold 100 megabytes. So that's a huge increase, right? So that's what that looked like. And later on, iOmega came out with another zip disk that could actually hold 250 megabytes worth of stuff, right? And these, I remember back in the day, cost about $10 each. So it was more expensive, but it wasn't like crazy outrageous. And what you would typically do is you'd have like a zip drive. And my first one, I was in grad school working on my master's degree. I had one of these external zip drives that would plug in through the parallel printer port on the computer. You could also plug it in through a SCSI port if you had a SCSI port, but the parallel port was the more common one. And you plug it in that way. This is before USB. There was no USB to plug something into. So anyway, I'll pass that around. There was also this phenomenon called the click of death that was associated with the zip disk. If you had a zip drive that was defective or that was messed up, what it would do sometimes is you'd put your zip disk in and you'd hear this loud click. And if you heard that loud click, that was a really bad thing, because what it meant was that it basically just killed your disk. And so whatever you had stored on that, it was gone. It basically killed the disk. You weren't able to access it anymore. And so that actually happened to that one that I'm passing around. If you see it says dead zip disk on there. I'd used it in a computer lab over at Commerce that had zip drives on all the computers. And this one particular computer had a bad zip drive, and it killed it. So that was like that sinking feeling that you'd get when that happened. But anyway, once USB technology took over and we started having USB flash drives, that basically made those things obsolete pretty quickly. So that's why you don't see them anymore. Had you ever heard of one of those before, unless you were in the Java class? No? So they were really popular there for a short amount of time. iOmega sold a lot of them. iOmega also had this thing called a Jazz drive at the time that was kind of cool. It was more of like a little tape technology, if I remember correctly. Yeah, it wasn't that. It was more like that. I think, was it tape? That's a zip disk. But anyway, so a tape is another technology, right? Like this. So back before we had larger capacity hard drives and stuff like that, a lot of companies would store or backup files and programs onto reel-to-reel tape. Computers, storage tape, maybe? Yeah. So it was like this, and you'd put it on a reel-to-reel tape machine, kind of like that. And that's how they could store files and stuff. But tape technology is sequential in nature, right? So just like a videotape or an audio tape is, right? So if you want to get to a certain file or a certain place on the tape, you have to fast forward or rewind to that specific location on the tape. So it can be incredibly slow to do that. But the upside was that it was a lot less expensive, and so that's why they used it. So this one dates back to, it doesn't say. This one says, I think it's 83. I think 1983. Advanced Structured COBOL. So I'm going to pass that around. Also, my very first computer, back in my day, we had my very first home computer when I was a kid was a Commodore VIC-20. And the Commodore VIC-20, we didn't have the floppy disk drive for it. We had an audio cassette disk or audio cassette storage, and it used regular audio tape. Commodore 64 tape drive. It'd be the same type of thing, but ours is a VIC-20. It was like the cheap version, but it looked like this basically. It looked like a tape player, audio tape player, but it wasn't. It would you'd store files on a regular audio cassette, and what was even funnier, you could actually take that audio cassette and stick it in a stereo and listen to it. It basically sounded like a modem, like modem sounds and stuff like that. But that's how it stored stuff. So anyway. All right, let's move on. Let's talk about, well, before we move on real quick, there's also optical disc technology, right? So this is a CD, CD-R. So these were great because you could store a lot on here. Like this could store 700 megabytes, right? But typically the downside of CDs was you write stuff to it, but they're not really usually designed for you to delete stuff off of the CD and replace it with new things. So they were great for backing up data and files and things, but not necessarily for storing things and deleting them, stuff like that. So although they did have like CD-RW drives and disk that you could delete, they worked a little bit different, but you had to have the special CD-RW drive to do it, and those weren't as common. So, and of course, it uses different technology, right? It uses lasers to burn pits and stuff in the disk and to read it and stuff. So, and these days they have you have your DVD technology and stuff that you can store onto optical disk in a similar type of way. All right, how about input and output devices? I'm going to try to speed up a little bit here. Input-output devices, obvious things are things like the keyboard and the mouse. Everybody knows what those look like. Here's an input device that you see every once in a while, but not that often. This was a trackball, right? So it's kind of like a old school mouse turned upside down. So instead of moving the mouse around, you move the ball. So you can move it with your thumb, and you have the buttons like that. But they still make trackballs. You can find them if you go to like Staples or Best Buy. Usually they have like a whole section with your input devices. And so there's some pretty cool devices out there. Logitech and Microsoft, they make some pretty cool stuff when it comes to input devices. Just search for a few. Trackball mouse. So here's some newer looking ones, right? They have, of course, if you have a laptop, you're going to have a trackpad, right? They make wireless keyboards. Bluetooth keyboards and stuff like that, and I know Logitech has some that have like the trackpad built into it. I've got a couple of those at the house that I really like. Yeah, this has been a big seller for them, I think. You can find them at Walmart. Right, it's got a little trackpad. And it's great for like if you have some kind of computer set up connected to your TV, and you want to control it wirelessly and stuff like that. So, and you don't have a flat surface to use a regular mouse. You've got the trackpad here and you've got the keyboard there. So those things are pretty cool. Other types of input devices, right? It might be a webcam for video input. It could be a microphone like this USB condenser mic that I've got here. A secondary storage device could even be input device because you get input from it, from like a hard drive or something, right? A scanner. Everybody knows what a scanner is for scanning documents, and they have all kinds of different scanners these days. I think I've got one in this drawer, actually, but it's big. I don't want to get it out. Output devices allow you to get feedback from the computer, right? So the obvious output device is a computer monitor, but it could also be things like your printer, a secondary storage device to write output to like a hard drive or something like that. Speakers, to get sound output. So without input and output devices, computers are pretty useless for humans, right? One early day home computer was the Altair 8800. Have you heard of that one? The Altair 8800 had no keyboard, mouse, or monitor screen. It was basically a box, and it was sold as like a home kit that you could put together yourself. It was popular with hobbyists and stuff like that. So how do you get input and output with it? It had, look at that picture. It had switches for doing some input on it, and it had these lights and stuff for output, right? So anyway. All right, moving on. Different types of software. So we have system software and application software. System software are programs like that interact more closely with the hardware. So it includes things like your operating system, like Microsoft Windows, or if you have Mac, you have the Mac operating system. If you have an iPhone, you've got iOS. You've got an Android phone. Android is your operating system for that platform, right? But it basically does things like manages the memory and input and output activities and stuff like that. That's what your operating system does. Other system software includes things like antivirus software, utility programs like disk defragmenters, system monitors, stuff like that. File compression tools. Application programs, that's what we think of as software most commonly. So that includes things like your office software, word processor, spreadsheets, databases, PowerPoint, stuff like that. Also includes things like video games or even the programs that we're going to be writing for this course. All right. Let's see here. All right. So computers are electronic devices, and so they have electricity running through them. Electricity is either on or off, and so computers are designed using a binary system. So if you look at machine language or the instructions, the actual instructions that get executed by the computer, they're all going to be in ones and zeros. We as humans don't interact with that very well, so we've developed things like assembly language and higher level languages like C++. But when we're talking about it, a single binary digit, a single 0 or 1, we call that a bit, right? And we use collections of bits to do things like represent information or data, and also to represent instructions that are going to get executed. And so common collections of bits are things like 1 byte. 1 byte is 8 bits. So with 8 bits or 1 byte, you can basically represent, there's like 256 combinations of ones and zeros, right? 2 to the 8th power, right? So with one byte, you can basically represent a character, or you could represent a number from 0 to 256, for example, or 0 to 255, really, technically, right? So if you want to be able to store a number that's larger than 255, you need more bits, okay? And so these are some common collections of bits and units of measure that are associated with those. So, and they're all based on powers of 2, and so that's why you see these actual numbers out there. But we usually kind of approximate them. So like 1 kilobyte is around 1,000 bytes, right? So, or around 8,000 bits. But technically it's 1,024 bytes. A megabyte is around 1 million bytes. A gigabyte is around 1 billion bytes. Terabyte is around 1 trillion bytes. And then they get into these others like petabyte, exabyte, and zettabyte that are larger. One thing that we'll talk some and use this semester in C++ programming is this thing called ASCII. And so ASCII stands for American Standard Code for Information Interchange. And what it is basically, it's a standard that has like basically 128 characters plus another 128 if you count the extended ASCII set. It's basically a collection of 8 bits and the different combinations of 8 bits that are designed or defined to represent different characters and different things. All right. So for example, the capital A, uppercase A, they say is actually stored in computer's memory as 10000001. Okay, it has an ASCII value of 65 if you convert that binary number to decimal. Right, it's actually the 66th character in the ASCII set. So we'll be talking about ASCII when we start getting into data types. And there's an ASCII table in your book, and I've got one that I'll probably pass out in class as well. Right. So probably next time we'll spend a little bit of time talking about number-based systems like binary or base 2, and as opposed to base 10 decimal, and so we'll look at how to convert those. Another common character scheme or character standard is Unicode. The Java programming language uses Unicode, and it actually reserves more bits. It reserves 16 bits, and so that gives you around 65,000 combinations of ones and zeros. So there's like 65,000 something different characters in the Unicode standard. All right, let's see here. So I'm going to try to speed up a little bit. Let's talk a little bit about programming languages and why this doesn't work for us very well. So machine language, if you're looking at machine code and machine language, you might have like these 3 instructions. If you want to do just something simple like do a simple multiplication and store that result in like a variable. So this would be like calculating somebody's pay, right? Wages is equal to rate times hours. So in machine language, it might look something like this. So there might be like 3 different steps. Maybe you load the first thing into a memory register, and then you multiply it times another number, and then you store that result in another memory register, for example. So it might look something like that. Well, I don't understand what that means. So there's something called assembly language, And the idea with assembly language is we can replace each one of those machine language instructions with something that looks a little more like English. And so it might look something like this. So the instructions might be like load rate, mult hours, store wages. So, but it's still the same number of steps. For every one machine language instruction, there's one assembly language instruction. So it's still really low-level stuff. It takes several instructions to do basically anything in assembly language. But you have to have this thing called an assembler that will translate that assembly language code into the machine code, into that. And that's what gets executed by the processor, right? But that's still kind of tedious to use, and so we've come up with high-level languages that basically allow us to do something like this. Wages is equal to rate times hours in one instruction. So one higher-level language instruction might translate to, several different lower machine language and assembly language instructions. But you have to have, just like with assembly language, you have to have some software that will translate your higher level language code into machine language code. And so with C++, we have something called a compiler. So the compiler will translate that high level language code into machine code. Right? And similar type of thing for other programming languages, such as Fortran, COBOL, Java, C#, Python, or whatever it happens to be. There are some languages that are compiled languages, and some that are interpreted languages, and it has to do with how the translation takes place. So, like with a compiled language like C++, it takes your entire source code, translates the whole thing into machine language code, or object code, sometimes they call it in the C++ world, and then that actually gets run. Right? So compiled languages typically run really fast once that translation is done, right? That's the catch. The other type of language is an interpreted language. With interpreted languages, it kind of translates and executes the program on the fly. So it will take one instruction, translate it, and then execute it, and then takes the next instruction, translates it, and executes it, takes the next instruction, translates it, and executes it, like that. Interpreted languages include things like a lot of your scripting languages, like Perl and PHP and shell scripts. Even the original BASIC programming language was interpreted, I believe. Right. Does that make sense? That difference there? All right. I might hit some of this next time. I'm gonna let you guys read this. This is talking about basically the steps that we do to write programs and stuff. So you can look over that. I'm running a little low on time here, I think. Yeah. Some things involved with problem solving and writing algorithms. An algorithm is a step-by-step series of instructions that will solve a problem in a finite amount of time, right? So basically, the process is something like this. We've got a problem that we want to solve, and we want to write a computer program for. So the first thing we need to do is understand the problem. So we analyze the problem, maybe even outline some of the requirements. Then we come up with an algorithm that basically is used to solve the problem. And this algorithm isn't written in the programming language yet. It could be like pseudocode. It could be a flowchart. It could be a structure chart or something like that. And then we take that algorithm, we implement it in a programming language, right, like C++ or Java or whatever, and then we verify that it works, test it, and then we use it and maintain it after that. Right. And so this is a little bit more information about those steps. Right. Let's skip that as well. And so let's talk about this real quick. Structured programming as opposed to object-oriented programming. In this course, we're going to focus on structured programming. And Programming Fundamentals 2, that gets more into the idea of object-oriented programming. If you're in the Java class, we kind of do both, right? Structured programming, the idea is to take a big problem and split it up into smaller subproblems. So it's kind of like divide and conquer type of approach. Sometimes they call it top-down design or stepwise refinement, modular programming. But the idea is to break a big problem into smaller subproblems. Right? The idea with object-oriented design, it's kind of hard to describe until you actually get to it. But you basically solve problems. You focus more on your data and building of user-defined classes or data types, and you build all the functionality into those data types and those classes. And then you have objects, which are instances of classes, and you solve problems by having objects that interact with each other. So, like I said, it's kind of hard to describe until you actually get into it. But it's a different way to solve problems, especially when they get to a certain level of complexity. All right. I'll talk more about that. We'll end with this. So a little bit about the history of C++. Well, where does C++ come, and what's up with that funky name, right? So the history of C++ and it kind of its origins date back to the history of the Unix operating system, right? So back in the late 1960s, I guess it was, and it's not on here, early 70s, probably late 60s, I guess. At AT&T Bell Labs, they were working on a new operating system called the Unix operating system. Perhaps you've heard of it. And they were writing this thing in like assembly language code, and it was kind of a pain in the butt to do. So there was a guy named Dennis Ritchie that was instrumental in developing of the C programming language. And it was kind of based and similar to another language that he had some experience with or had seen, I think, and that was called B. So the next letter after B is C. So real imaginative there, right? So it doesn't really stand for anything, I don't believe. So anyway, they wrote the Unix operating system kind of with the combination of C code and assembly language code. And so C was a very popular language and still around. And but in the mid-'80s, 1980s, they also at AT&T Bell Labs, they wanted to make some improvements and add some features to the C language. So they did that, and one of the main guys was named Bjarne Stroustrup, which I believe he's still living. He was working as a professor at one point in time down at Texas A&M University in College Station. But anyway, they added some features such as support for object-oriented programming and abstract data types back in the mid-'80s. And so in C, in the C language, if you want to add one to a variable, like x, for example, you could say x++, and it adds one to it and assigns it back to itself. So it's an incrementation of a variable. So again, I guess they're being clever. So an incrementation of the C language is C++. So that's where that comes from. And in the late 90s, they standardized some things and kind of came out with this ANSI ISO standard of C++. I remember that. And then they've also, come out with new standards and stuff over the years. So anyway, that's kind of where it came from, C++. There's other languages. There's one called C#. This is more of a Microsoft technology. It's really good. It's really good for things like I think it's better for like GUI, graphical user interface stuff, and but it's more of a Microsoft technology anyway. So that's a little bit of history there. All right, and so this is just kind of a summary review thing about what we talked about today, about some different types of hardware, and compilers and algorithms, and structured and object-oriented design. Cool. Anybody have any questions about any of that? Thanks for hanging in there with me. Again, I apologize if you got a double dose of that from the Java class. If there's anything up here that you want to check out, any hardware things, feel free to check it out. And so for next week, if you need to look over chapter 1, feel free to do that. But also be reading chapter 2, because that's what we're going to focus on next week is chapter 2, and it's very important. The basic elements of C++. We'll talk about things like identifiers and data types, and some basic rules, also arithmetic operators, and a little bit of math, basic math, like elementary school math, but it's the main focus is on how the computer thinks, right? And we'll also talk about some basic input and output, and hopefully we'll have time to maybe write our first computer program. So. All right, that's it.